Hi, this is Sally's Book Club. Tune in daily for global literary gems curated just for you. Today we're exploring the book Driverless. Over the past century, cars have transformed our lives, weaving mobile networks through every street and alley, have brought travel convenience while creating countless jobs and social opportunities. But this mobility comes with challenges: traffic accidents, congestion, pollution affecting us all. Ever imagined human-driven cars becoming obsolete, replaced by autonomous vehicles? Your first intelligent robot might be your car. Entrusting your life to it sounds futuristic, doesn't it? Tech giants like Google, Uber, Tesla, Baidu already joined the autonomous vehicle race with promising results. You might soon witness this groundbreaking technology emerge. Why has this autonomous driving wave emerged now? What are the implementation challenges? How will it transform our world? After listening to Driverless, you'll gain insights into these questions. Driverless by Hod Lipson, Columbia AI Lab director, and Melba Kerman, LA Times calls it the go-to book for accessible, intelligent coverage of autonomous vehicles. Professor Lipson's work stands as the perfect choice for general readers. The Chinese edition spans 250,000 words. We'll explore it through three perspectives. First, what does an autonomous driving world look like? Second, what technologies enable it and what challenges remain? Third, what impacts would full implementation bring? Let's begin with part one. Envision streets filled with coordinated autonomous vehicles, moving like schooling fish, seamlessly avoiding obstacles while maintaining high-speed flow. Need a ride? Just tap your phone, and an autonomous vehicle will arrive to take you anywhere. Want to carpool? You might share the ride with 1 to 2 passengers heading your way, reducing travel time and costs. Shorter commutes mean people can live farther out. Your car self-parks safely until needed again. No more circling for parking spots, plus lower transportation expenses overall. Smoother acceleration or braking cuts fuel use by 15 to 20%. Vehicle platooning reduces wind resistance for extra savings. When will this future arrive? The transition won't happen overnight, but through gradual stages. Analysts predict first consumer autonomous vehicles by 2025. 10% of global new car sales could be autonomous by 2035, rising to 80% by 2050. But legacy human-driven vehicles will still make up 40 to 60% of road traffic. Humans and machines will share roads for decades to come. Two major public concerns persist about this autonomous future. First concern: autonomous vehicles aren't safe. Machine safety depends on how you define safe. Zero accident perfection is impossible, now or ever. But statistically, machines outperform human drivers. Most human-caused accidents involve preventable factors: human errors, DUI, drug impairment, fatigue, distractions. Autonomous systems eliminate these risks through hive-mind learning. One machine's learned lesson becomes instant knowledge for all, an unmatched advantage. Though current autonomous tech remains in early stages, machine learning efficiency grows exponentially. The second concern: autonomous development requires massive infrastructure investment. This misconception stems from 20th century US DOT plans installing road transmitters for vehicle vision, like the fable where a king ordered leather-paved roads to prevent foot discomfort. Wildly expensive. The solution came through shoes instead, achieving the same effect through different means. Autonomous tech follows this logic, embedding vision systems in vehicles rather than roads, minimizing infrastructure needs. General Motors developed the first autonomous car prototype in 1939. Decades of fluctuating enthusiasm followed, with various approaches emerging. Why has true progress only come recently after all these years? Let's explore the technical challenges through three driving components. First, sensory organs: eyes or ears, gathering environmental data, perception. Second, brain processing information and issuing commands, decision-making. Third, body executing vehicle control, implementation. Thus, autonomous systems require perception, decision-making, upper control, and execution systems. The perception system, mid-level control, handles environmental recognition and analysis. Let's focus on this crucial perception system first. An intriguing biological theory relates to this, the light switch theory. It suggests photosensitive cells triggered the Cambrian explosion by enabling complex life development. And similarly, in autonomous driving, the creation of eyes proves crucial. An autonomous vehicle's eyes include digital cameras, LiDAR, radar, sensors collecting speed data, directional information, pedestrians at intersections, speed limit signs, and traffic indicators. These provide comprehensive environmental data for the perception system. Digital cameras remain the most affordable and widely used sensors. Their color recognition capability makes them ideal for scene interpretation compared to radar. They excel at recognizing speed limit numbers and traffic light colors through image processing. But limitations exist. Lack of stereoscopic vision prevents accurate distance measurement, and extreme lighting conditions severely affect image quality. The 2016 Tesla autopilot crash, where strong sunlight caused system confusion between white truck and sky, demonstrates this vulnerability. Current camera systems often fail in such extreme scenarios, compromising decision-making. LiDAR and radar compensate for these camera limitations effectively. LiDAR uses pulsed lasers to measure distances through reflection timing, creating precise 3D environmental maps. Its short wavelength detects minute targets over long distances with high accuracy. Measurement precision depends on laser beam count. More beams mean broader simultaneous coverage, like using multiple paintbrushes. More brushes cover larger wall areas faster. Most test vehicles currently use 64 beam LiDAR systems, comprising 64 lasers, rotating 10 times per second for 360 degrees coverage. Though costing tens of thousands of dollars, these remain essential components, making LiDAR technology a battleground for sensor manufacturers. Now let's discuss microwave radar. Similar in principle to LiDAR, but using radio waves instead of lasers. This mature technology powers highway speed cameras and vehicle collision warnings. While less precise than LiDAR, its affordability, compact size, and ability to penetrate fog or smoke make it weather resistant. Cameras and radars complement each other, providing comprehensive environmental data for autonomous systems. With sensory inputs established, the next challenge becomes interpretation. Is that stationary object ahead a pedestrian or traffic sign? The system must decide, can it predict movement? How to filter crucial data from sensory overload? This demands human-like cognition, processing information through recognition and analysis. This represents the core of modern AI advancements. Traditional AI used top-down, rule-based programming with predefined if-then logic. What constitutes an appropriate response in each scenario? This approach had significant limitations. Machines couldn't exceed programmer-defined parameters. Their capability ceiling depended on human expertise. Real-world scenarios present infinite variations beyond finite programming capabilities. The watershed came in 2012, when deep learning models dominated ImageNet's image recognition competition. AlphaGo's 2016 victory over Lee Sedol brought deep learning to mainstream attention. Unlike traditional programming, deep learning employs bottom-up, data-driven learning. Systems learn feature recognition through massive dataset training rather than explicit programming. Deep learning software identifies cats by studying thousands of images, maybe recognizing pointed ears, whiskers, or fur patterns. It detects feline features across different scenarios through these learned characteristics. How does deep learning achieve this? The answer lies in artificial neural networks, powering everything from license plate recognition to iPhone Face ID. Biological neural networks transmit signals through neuron layers when stimulated, like feeling pain from a pinprick. Each neuron decides whether and how strongly to fire signals. Artificial neural networks replicate this through layered computational nodes. These algorithmic nodes adjust weighted parameters to determine signal transmission. Take cat recognition. An image enters the input layer for weighted calculations. Signals pass through hidden layers via successive computations. The output layer's single neuron answers with 0 or 1. Is this a cat? 1 means yes, 0 means no, zero point 0.5 indicates uncertainty. Incorrect answers trigger parameter adjustments for improved learning. Through this process, autonomous vehicles distinguish crossing cats from fallen cardboard boxes. Thus, the perception system combines sensors with deep learning, the soul of autonomous awareness. This integrated approach provides crucial environmental understanding for self-driving technology, moving from mid-level to upper control systems, deciding stops at traffic lights, route choices at intersections. Should we detour around the river ahead? These are upper control system challenges centered on path planning and navigation. You might think of consumer navigation apps, but autonomous vehicles use specialized maps. They rely on HD digital maps rather than standard navigation maps. The key differences lie in precision and data density. Standard maps have meter-level inaccuracies, acceptable for human drivers. Human visual processing compensates for these imperfections naturally, but machines require centimeter-level precision in HD maps. HD maps provide 3D coordinates for lane markings, infrastructure, and obstacles. Beyond coordinates, they include detailed road attributes, dashed or solid lane lines, road gradients, barrier types, all meticulously defined. These parameters create safety-critical databases with millions of data points. More detailed maps equal higher vehicle safety margins. Such map creation requires massive resources and manpower. Currently, only well-funded corporations possess HD mapping capabilities, but future possibilities suggest alternative approaches. Advancing sensors and AI could reduce dependency on pre-mapped data. Real-time environment recognition may eventually surpass static map reliance. Autonomous fleets could crowdsource and maintain map data dynamically. Another key technology emerges: V2X, vehicle-to-everything systems. V2X creates an IoT network connecting vehicles with their environment. This includes vehicle-to-vehicle, V2V, and vehicle-to-infrastructure, V2I, communication systems. Imagine vehicles receiving real-time traffic light data, guaranteeing zero red light violations. Knowing surrounding vehicles' intentions could prevent accidents better than LiDAR sensors. However, network connectivity introduces cybersecurity concerns. Real-time responsiveness, transmission reliability, and data security are V2X's critical challenges. Combining HD maps with V2X enables smart routing algorithms evaluating traffic lights, congestion, roadworks. Now let's discuss implementation systems. After perception and decision-making, execution systems convert commands into physical actions. If upper controls handle cognition, lower controls manage reflexes, steering, and acceleration. Engineers use drive-by-wire systems replacing human pedal steering inputs. Multiple processors control mechanical systems through specialized subsystems. ECU, ABS, TCU, etc. These communicate via CAN, controller area network bus systems. The control principle remains fundamentally simple. Take cruise control. Increases fuel injection when speed drops below target. Reduces fuel supply when exceeding speed limits. So what's challenging about execution systems? Precision and responsiveness are paramount for autonomous control. First challenge: high-speed data transmission through vehicle buses. Control smoothness directly impacts passenger comfort. Ideal execution feels imperceptible. No abrupt speed changes. Her execution feels like riding a roller coaster. Network security remains crucial. A compromised CAN bus could let hackers hijack vehicles. Like that Fast and Furious movie scene where cars go berserk. Potentially real-world risks. Let's summarize our second section findings. We've examined autonomous tech through perception, decision-making, and execution frameworks. Sensor arrays, HD mapping, and CAN systems all depend on exponential chip advancement. explaining why now's the breakthrough era. As chip capabilities grow, autonomous development will accelerate rapidly. What societal impacts will full implementation bring? Our third section explores this. First, the benefits. Primary advantage, time reclamation. Drivers become passengers, no more school runs or spouse commutes. Your autonomous vehicle handles all transportation duties. Reduced travel time through optimized routing and congestion prediction. Second benefit, enhanced mobility experience, on-demand availability, safer rides, and inclusive designs aiding elderly or disabled users. Third, dramatic accident reduction. Studies predict 80% crash reduction with 90% autonomous adoption, saving millions of lives. Fourth, environmental benefits through optimized driving patterns, reducing emissions. This utopian vision raises crucial questions. Will achieving autonomy truly mean problem-free transportation? Now let's examine autonomous driving's hidden crises. The liberation from manual driving also eliminates driving jobs. Truckers, taxi drivers, blue-collar jobs resistant to previous automation waves now face extinction. Auto insurance industry will shrink as safer machines reduce premiums, impacting billion-dollar markets. Worst case scenario, autonomous tech could decimate industries and widen wealth inequality. Another critical issue, data security concerns. Imagine every movement tracked, identities, locations, companions recorded in detail. While ubiquitous surveillance deters crime, it erodes personal privacy completely. Lastly, social isolation paradox. Time-saving convenience reduces human interaction. Commutes lose their role as bonding opportunities, like school runs with children. Autonomy might deprive us of these precious interpersonal moments. Convenient travel could deepen modern loneliness epidemics. Future autonomous pods might offer social matching features, pairing passengers based on shared interests to combat isolation. As the authors note, autonomous cars may become our most disruptive machines. Rather than resisting, embracing this change might transform lives profoundly. We earnestly hope this transformation proves beneficial. That concludes our exploration of driverless. Key takeaways are available below the audio. We'll meet again tomorrow. Until then,